Here we have the electron deflection tube, but in this video I'm going to show you it with a magnetic field. In the previous video we saw how the electron beam was deflected by an electric field. This one we're going to deflect it using a uniform magnetic field. Right, the thing that's producing the uniform magnetic field in this case are these circular coils you can see there. Now these are called Helholtz coils. If I just rotate that slightly, you'll probably see that a lot better. But literally we've got two large radius coils parallel with each other, with the planes parallel to each other. Now the gap in between is going to be a uniform magnetic field. As long as the current is flowing the same direction through each coil, okay, then you'll have a north on one side, a south on the other, a north on one side, a south on the other, so there'll be a uniform magnetic field going between the two coils. Okay, the current passing through each coil comes from these two DC power supplies here. Now I've got they're connected in series with the two coils, and I've got an ammeter in series as well to see the exact current flowing through each coil, because I think maybe you can see on the front there, the maximum current that those two coils can take is 2 amps. If you go any higher, they're going to overheat. If they're going to overheat, there's a chance of them melting or breaking, and then it's game over for the Helholtz coils, which we don't want. Anyway, if we turn on both power supplies and wait for the voltage to go up, we can see a current, so 0.16 amps flowing through the coils now. So if I turn up one of the power supplies, you can see the current going up to 1.15 amps. If we turn up the other one, turn up the voltage on the other one, so these two are in series with each other, like two cells in a battery. We can see we can go up to right about 2 amps. Okay, so that is going to be our setup for producing the uniform magnetic field around our electron deflection tube. Okay, so if I just put that back to the way it was. Now, as explained in the previous video, the electron deflection tube consists of 3 parts really. You've got the heater here, which this is where the electrons are emitted using thermionic emission. So that's connected to the DC power supply here. If you remember, 6.3 volts. Any higher than that, and you're going to knacker this, which we don't want. So the electrons get produced here. Now they are accelerated here in the electron gun. They're accelerated down because we have, I don't know whether you can see that, let me rotate that again. You can see there, okay, we've got to the back here, connected to 2, this fell here, to the EHT. So the EHT, this cable here, this is the plus 5,000 volts. That's going to go and get connected to the electron gun in the electron deflection tube. So let's just put that back to the way we want it so we can view it. Okay. So this is the cable here. This is going to be connected to the plus 5,000 volts. So yeah, DC power supply, that's for the heater here, that just needs to be 6 volts. EHT plus 5,000 volts, that's accelerating the electrons here. They go through the gap and then they hit the screen there. Okay, and it's the magnetic field that we want to be interested in. So let's turn off the Helholtz coils for now. So we always start with zero magnetic field. So let's turn on the heater. Okay, really don't want to be going any higher than 7 volts with this, so let's take it up to, that'll do. Play safe, 6 volts. So electrons now being emitted here. We now want to accelerate them in that direction. So we turn on the EHT and let's take that up to maximum, 5.3 volts. And as you see there, the electron beam is going straight through the middle. If I turn the lights off, we might get a better view of the electron beam. There you go. So there's your blue electron beam right down the middle. That's better. Right. Okay. So it's now time to turn on magnetic field. So at the moment, with zero magnetic field, as we can see, the electron beam's going right down the middle. If I turn on, the current in the Helholtz coils, if I turn on the uniform magnetic field, we should start to see the beam being deflected. I'll just zoom in for you. Right. Now what we're going to do now, we're going to turn up the current in the Helholtz coils. As you can see, the curvature of the electron beam is going to be increasing. So let's keep turning up the current in the Helholtz coils up to maximum. So if I just zoom out again, you can see right, we're up to 2 amps. There's 2 amps of current in the Helholtz coils, so we're now at our maximum current, our maximum magnetic field we can get. Okay. But if I zoom in and turn off the lights, you should be able to see the nice curvature there. Right. With electric fields, we saw the electron beam produce a parabolic curve. Okay? We saw the uniform electric field produce a parabolic curve. Now, the shape of the curve in a uniform magnetic field is different. The shape, which you should now know, is actually circular. It's a circular path. So if I just turn that off. So there you have it. That electron beam there is following a circular path. So that's a segment of a circle. Right, so there you have it. 5.2 kilovolts, accelerating the electrons into a uniform magnetic field to show the circular path of electrons in a uniform magnetic field.